Review what we talked about on Thursday. So let's review what we talked about in class on Thursday. So what we're going to do is we're going to extend what we've talked about in terms of calculating the electric field due to a set of point charges into how we can talk about calculating the electric field due to a continuous distribution of charge. So we said we know that if we've got a series of point charges, so here's Q1, Q2, Q3, in this case we'll let them all be positive, then all I need to do is I need to add up the electric field contribution from all three of those charges at point P. And that the electric field at P is just going to be the vector sum of the contributions of each of my individual point charges. So I'm going to sum up over however many point charges I have. So I've got I point charges, so I'm going to do some basically vector addition over I vectors. Right? And I know that I can calculate the magnitude of each of those vectors by using kq over r squared, and then I need to take care of the directions when I do the vector summation. So if I've got a continuous charge distribution, and all that is just a fancy way of saying that I've got something that I very clearly can't treat as a point charge. So whatever this strange object is, it has volume. So it stretches out in 3 dimensions. It's very clearly not a point charge. So what I can do then is basically I can say, well, let's break it up into tiny little charge elements that I can treat as point charges. And so here I would pick some tiny little charge element dq. It's going to have some amount of the total charge that sits on my on this charge distribution. It's going to generate some contribution to the electric field at point P. Again, the line that connects my little charge element to point P, that's going to be the contribution to the electric field from that charge element has to lie along that line. And then what we would do is basically sum up over all the possible little charge elements that then make up whatever this large continuous charge distribution is. So the way we're going to do that is, instead of having a discrete number of things to add together, we now need to add together an infinite number of infinitesimally small point charges, and so we're going to do that with an integral. Now, of course, if we have a charge distribution that's stretched out in 3 dimensions, then this is really a triple integral over volume, right? So I would have some stuff that's going in x, stuff going in y, stuff going in z, and would need to integrate over all that to get the total contribution to the electric field at point P. And again, I can figure out what the contribution from each little charge element is by thinking about this right here. So I need to add up k dq. dq is the amount of charge in my little charge element over r squared. And then again, I've got to add these up as vectors. So the r hat is going to matter. So to do this problem is actually very, very similar to the problem we've been doing. We just need to use the integrals to add up over all of our little charge elements rather than a summation over all of our discrete point charges. But otherwise, the process is going to be very similar. So just to review, what was that process? Well, we would draw a sketch, then we'd draw the vector diagram showing all the field contributions from each of our point charges. We'd pick a coordinate system. We'd break those field vectors up into components. We'd set up the vector sum equations. We'd get to do one per dimension. We'd calculate the magnitudes and plug those in. We'd solve for the components of the net field. We'd Pythagorize to get the magnitude, and then we'd use inverse tangent to get the direction. So this is basically the process that we've been using to calculate the net electric field for multiple point charges, and all we're going to do is just alter it slightly to deal with our charge distribution. So we're going to start the same way by drawing a sketch, and now we're going to draw the vector diagram of the field due to one infinitesimal chunk of charge dq. So we're going to pick some dq, some just random point out there in our charge distribution. We're going to draw its contribution to the electric field at point P. We're going to pick a coordinate system. We're going to break that little our little dE vector, the contribution of our infinitesimal charge that we've selected, our charge element that we've selected. We're going to break it up into components. We're going to set up our integral equations. Again, there's going to be one per dimension in the problem. We're going to calculate the magnitude of dE and trig functions that we'll need to break this vector up into components. Then we'll solve for the components of the net field by dealing with those integral equations. If we need to, at that point, we can Pythagorize to get the magnitude, and we can use the inverse tangent to get the direction. So again, it's a very, very similar process. Really, all we're doing is we're focusing on a single charge element and its contribution to the electric field dE, and then we're going to break that up into components and integrate over our two equations. So just as an example, and just sort of walk through this. So you'll notice we said that one of the things that we're going to do is we're going to keep our life relatively simple in dealing with these integrals, and so we're just going to deal with lines of charge distribution. So here I happen to have some total charge Q sitting along a line of length L. Here's the point P that I'm interested in. Notice that L in this, my line in this case lies along the y-axis. P is some distance d away along the x-axis. And so the first thing I'm going to do is I'm going to pick some tiny little charge element dq, and I'm going to draw in the contribution to the electric field at point P due to this little charge element dq. So here's the contribution to the charge element I've chosen, contribution to the electric field at point P. Okay. Since this whole thing is positively charged, that means that each little element of it is going to end up being positively charged, and so that's why I know how to draw the direction here. Right? The electric field will point away. It'll lie along the line that connects the little charge element I chose to the point P. So this is my contribution that now I'm going to care about. Choose a coordinate system. Well, in this case, basically our coordinate system was already given to us, so positive x is going to point to the right, positive y is going to point up. And now I need to break up that vector, break up this vector into its components. So there's two components. There's one in the x and one in the y. So I'm going to pick an angle here, and I'll let this angle be the angle theta. And again, I'll notice that this is going to give me a right triangle that I can use to figure out what's going on with theta in a couple of steps. And so there's going to be an x component of that contribution and a y component to the electric field contribution. And so given my choice of angle theta, the x component is going to get the cosine of theta, the y component is going to get the sine of theta. So the two components that I'm going to care about here, in terms of the x and y components of this contribution to the electric field for my little charge element, dE, is going to be dE cosine theta for the x component and dE sine theta for the y. So set up my integral equations. Again, I got stuff going on in 2 dimensions, so I'm going to have 2 equations. And in this case, it's basically saying, well, since my line starts at y equals 0 and goes until y equals L, then I'm going to have an integral from 0 to L in both cases. And so I'm just going to add up the contributions of all my little dq's, starting with sort of my tiny little charge element down here and going all the way to my tiny little charge element up here at y equals L. So that's all these 2 equations are telling me that I need to do, is just add up the x contribution and the y contribution over the entire length of the rod from 0 to L. All right? So now I need to calculate the magnitude of that field contribution and then the trig functions that I need to plug into my 2 equations. So I know that the magnitude of my little field contributions given by dE equals k dq over r squared, and we said there's sort of 2 pieces that I need to deal with here. So k is just my Coulomb's constant. I need to deal with what is dq, and then I need to figure out what is r squared based on the geometry in my problem. So dq, we said there are 3 options. So it's either going to be lambda dx, lambda dy, or lambda r d theta, where again lambda is just some description of the charge per length. Right? So maybe it's constant, in which case that would just be total charge divided by total length. Maybe it's some functional form that again we might be given within a problem. But we're gonna break this up into lambda, some charge per length, times a length, and the length that matters is, well, what's the length across the rod? And here you notice that my length, because the rod lies along the x-axis or along the y-axis, that this tiny little length is in dy. And so for dq in this problem, I'm going to want lambda dy. So you notice this is different from the example that we worked in class, but that's because we've taken our rod, and instead of the rod lying along the x-axis, now the rod lies along the y-axis. So that's why we've switched what we're plugging in for dq. For r squared, well, again, r is the distance from our little charge element to point P. So here's r. Again, it's the hypotenuse of this right triangle. This right triangle, well, let's see, dq sits at some height y. This length of our triangle is always d. And so I get from the Pythagorean theorem that r squared has just got to be y squared plus d squared. So I know what to plug in for dq, I know what to plug in for r squared, so when I do that, I get that my little, the magnitude of my little element electric field contribution is just going to be k lambda dy over y squared plus d squared. And so again, I can see that y here is going to be the variable of integration that I care about. I'm integrating from 0 to L in the y. I'm going to be integrating over dy, and so this y is going to be part of what I'm going to have stuck within my integral. All right, so that's the dE part. Now I need the cosine and sine theta pieces. Well, again, if this is my angle theta, and cosine theta is just adjacent over hypotenuse, well, the adjacent side to this angle is length d. The hypotenuse is r, so r is just take the square root of both sides here, and so I get that the cosine theta is just d over the square root of y squared plus d squared. Sine theta is going to be opposite, so that's the height y over the hypotenuse r. And so sine theta can just, in terms of the variables I care about here, can just be written as y over the square root of y squared plus d squared. So now I know what the magnitude of dE is, I know what cosine theta is, I know what sine theta is, so now I can go plug those into my equations and just solve. So for my x equation, I've got the integral from 0 to L, from y equals 0 to y equals L, of dE cosine theta. Here's dE, k lambda dy over y squared plus d squared. Here's cosine theta, d over the square root of y squared plus d squared. And so I've got, well, the k, that's just a number, that comes out. D in this case is a constant value, that comes out. And I'm left with this integral. And the only thing left to sort of care about is, well, what do I need to do with lambda? And there's one of two choices. So either you have a uniform charge distribution, in which case lambda is just q over L, and it can also come out of the integral, or lambda is going to be given to you as something that depends on y, and then you would leave it in the integral. So this, basically, once we figure out what we need to do with lambda based on what we're told about in the problem, this now becomes my integral that I need to integrate. Okay? For my y equation, it's exactly the same thing, right? So I'm going to integrate from y equals 0 to y equals L, dE sine theta, dE, same dE, k lambda dy over y squared plus d squared. Sine theta is y over the square root of y squared plus d squared. And so again, when I look at this, I can say, okay, well, the k comes out. Y needs to stay in. I've got dy, the y squared plus d squared term, that's got to stay in. And again, it becomes, well, what do I need to do with lambda? So if we've got a uniform charge distribution, then that's just a constant. It's q over L, and that can come out of the integral. Otherwise, we've got to have lambda as lambda will have some functional form that depends on y, and it'll be left inside the integral. And then again, we'll just integrate this equation. So that would give us the x and y components of the field, and then if we need to go further and get the magnitude, then we can Pythagorize those two components. If instead what we need to do is get the direction, then we can use the inverse tangent to get the direction. So that's the process we're going to use to solve these types of problems.